Hello, eighth graders. So we are now getting into our actual geologic time scale. And before we can talk about the geologic time scale, we have to talk about the things we actually use to determine this time scale. Just because obviously we don't know how old something is unless we actually know what something is. And the way that our Earth has preserved these records for us is through fossils. So let's keep moving. So we are working with two standards for this unit. We are working with Middle School Earth Science Standard 1-4 and Middle School Life Science Standard 4-1, which states that for the Earth Science Standard 1-4, you'll be able to construct a scientific explanation based on evidence from rock strata for how the geologic time scale is used to organize Earth's 4.6 billion year old history. And then the one that we're going to focus in on today is Middle School Life Science Standard 4-1, which states that you will be able to analyze and interpret data for patterns in the fossil record that documents the existence, diversity, extinction, and change of life forms throughout the history of life on Earth under the assumption that natural laws have always operated the way that they do now as they did in the past. So basically saying when something dies now and if its remains are left, that's where they're going to be, is somehow fossilized later. It's not like something changed where when dinosaurs died, their fossils then flew up into the air. That's sort of the idea behind it. So what you are going to be able to infer from this is the use of relative data and estimate of age of rocks using index fossils, but we really need to focus in on what is a fossil. That's the biggest point of today. So today you're basically just going to be at a 1 or a 2 for either of these standards because we need to understand what something is before we can actually use it. So make sure you for sure have either the whole group notes ready to go or the entire notes document ready to go. So let's talk about this. Who actually studies fossils and other ancient remains and all that kind of stuff? They're paleontologists. Paleontologists, archaeologists. It really depends on what form of ancient life they are studying. So if they're studying dinosaurs, it's a paleontologist. If it's studying any sort of human life, it's an anthropologist. Things like that. But we're going to focus in on paleontology just because we're going to obviously be looking at fossils and being able to actually date certain objects. So that paleontologists live off of the principle of uniformitarianism. That's basically just a big old word broken up to say it's the assumption that the same natural laws and processes that we are operating under today are the way it's always been. So the idea that, again, when something falls to the ground, it stays to the ground unless acted upon by another force. Things like that. It is, we have always fallen to the ground, we've never flown up into the sky as humans, sort of a thing. So that's kind of the whole idea that what happens naturally right now is what has happened naturally since the beginning of time. Another job of a paleontologist is to compare fossils to now living organisms. This one is the biggest. This is what we kind of talked about a little bit in 7th grade as far as looking at an organism such as, say, a horseshoe crab today and comparing it to what was once a trilobite. Now, trilobites no longer exist, but we have fossil evidence that there was an organism that looks a lot like today's horseshoe crabs. And so we can operate under the idea of, well, this trilobite must have done something similar to what our horseshoe crab does today, where mainly in the water, but can live on land for short periods of time, things like that. So that's the job of a paleontologist nowadays, because obviously if you're studying something that's extinct, you got to compare it to something that is currently living to be able to get an idea of how did this organism once possibly live. So this is the horseshoe crab compared to what a trilobite was. Very, very similar, and actually through fossil records, we've been able to identify that they are very closely related organisms. So now, as I have told my kiddos from the get-go, our whole lives are based off of theories. I'm not here to tell you one theory is better than the other and whatnot, but these are the two theories that we're going to live by in the realm of earth science and geologic time. So the first theory would be catastrophism. Okay, if you break that up, you have catastrophe. And a catastrophe is essentially like big events that end in a lot of death. So catastrophism is the idea that conditions and organisms on Earth have changed quickly thanks to violent events. This would be things like volcanic eruptions or flooding. These are not 100% supported by scientists anymore, but this was rather the idea of having a very young Earth. So if our Earth was only a couple thousand to 1,000,000 years old, this was a really great idea that really life has only been there since life started, died, started, died, started, died. Those sorts of things. What we now have more so moved towards, at least in the scientific community, is the idea of uniformitarianism. So the idea that geologic processes that are occurring today are similar to those that once have occurred in the past. So identifying that the Earth's crust is constantly changing. We know this through the theory of plate tectonics. We know this through the idea of Pangea. And just the fact that we are constantly creating new Earth today at mid-ocean ridges and destroying Earths at any sort of convergent zone, things like that. This is more supported due to the fact that we know, and we'll talk more about this, but we know that our Earth is at least 4.6 billion years old. We can date it back that far. So this is the idea that Earth is old and it's constantly changing, and it has been since the moment it was birthed. So those are two of the main theories that we're going to kind of be looking at. Obviously, like we have discussed in class, there are other theories that other ideas in our lives could support, and I'm not saying that those are wrong. These are just the two that we are going to focus in on within science class. So how do we know that our Earth is as old as we say it is? Well, we look to things such as fossils. So what this means is these are preserved remains or evidence of ancient life, things that once lived on this earth that may not be here anymore. More than likely, they're not here anymore. But the idea is that 99% of all organisms that once were are now fossilized to one extent or the other. So we look at evidence from a distant past or a not so distant past in order to really see how our Earth once was and what used to be here. So we need to understand before we break off into more independent work is that fossils are not necessarily the whole picture. Okay, so we have to understand that soft materials decay, they rot away. Things such as plant matter, soft tissue in animals. You know that when you're looking at a dinosaur fossil, you're not looking at their skin, you're not looking at their organs, you are looking at strictly their bones. That's because hard materials fossilize. Bones, teeth, shells, things like that. Those all fossilize because minerals are able to seep themselves in under a long period of time and replace what once was calcium and carbon and things like that, and now replace it with things like quartz and other materials like that. Soft material just can't last long enough. The difference between leaving, like, say, an apple on the counter versus like a bone, like bone marrow or something, like the apple rots away much, much quicker. So it doesn't allow for enough time for those minerals to actually seep in and replace what makes us, to be able to give a whole picture. So most fossils, now there are some that not necessarily follow this rule, but most fossils are just going to be the bones, the teeth, and shells if they have any. That's it. So this ends whole group, but if you are still listening because you are doing notes independently, great, let's keep moving through. So there are 5.5, 6-ish. It depends on how you look at two of these types of preservation that can be considered fossils. We have preserved remains, carbon films, mineral replacements, molds, casts, and trace fossils. Now, I'm going to explain each of these in depth and explain how some of them can kind of be paired up together, which ones are more like behavioral, which one is more actual, like this is a body fossil, things like that. So bear with me. Preserved remains. Now, this is where I don't know if you would necessarily call this a type of fossil, but rather the only time you're ever going to get soft tissues. So preserved remains is where the organism has been completely enclosed in some sort of material over an extended period of time, such as being stuck in a tar pit, being encased in amber, or completely being frozen in essentially a giant ice cube. So what happens is when the organism gets encased in any of these materials, it prevents extra exposure to air and to bacteria, which essentially the bacteria is what eats away at all the soft tissue matter. So after about 10,000 years at the absolute longest is where we see preserved remains still being intact. This happens to be a very, very young elephant that got stuck in a tar pit. And because its skin was completely encapsulated in this tar, it wasn't exposed to the air and the bacteria that would normally eat it away. So that's why we still see its entire outer skin. Now, open it up and the organs probably are no longer there because obviously we have enzymes and things like that within our digestive tract that would eat away at it because that's just what our body does. So things like that. So that's the first fossil. Again, you can call it a fossil, but it's technically just preserved remains. Carbon films. Carbon films is essentially when you get an organism, typically of soft tissue, stuck between two giant rocks. And it gets exposed to heat and pressure, forcing all of the gases and liquids that are just naturally within soft tissues to escape out, but leaving behind the carbon and the harder materials as almost like a picture. So a carbon film is like, you guys probably don't know this because you're way too young to have ever used like an actual camera with film, but it's like the negatives of a film strip where it's what remains behind before all the color, before all of the enhancements, things like that. But the only way this can happen is if this organism gets stuck in between two giant rocks being placed under heat and pressure, but not enough heat and pressure to start moving towards that metamorphism that would happen with metamorphic rocks, because obviously you're right to the point of completely melting, but you're not necessarily, it's too hot to keep the soft tissue to remain. So it's like a picture. Essentially, this is one of the few ways we can get more of those soft tissue materials fossilized. So this is an example of a fern that has gone through the carbon film fossilization process. Molds. So molds are kind of like how they sound. They are a mold. They are the impression in a rock that's left behind by an ancient organism. Typically, the organism itself decays over a long period of time, but this is the afterthought. So in this example, this is a shell. Now, this is the imprint of the shell that was left behind that if we cut it off, we could essentially say, hey, here's a replica of a shell. That sort of a thing. That's the idea of the mold. Now, the example I always use, and it's absolutely ridiculous, but some of you are totally going to get it. If you have a grandparent that insists on having Jell-O, now my G, I love my Gma. She is not a cook. She lives in a city for a reason. And when she brings a dish, any holiday that she's invited over for, it's always a Jell-O mold. So this is the actual Jell-O in this like fluted sort of a pan where it looks all pretty and whatnot. And yeah, so it's like a Jell-O mold. So if you imagine like the wiggly jiggly Jell-O in different shapes, those are molds. They were poured into something else and then came out as the replica of that shape. So that is a mold fossil. Now, you can't get a mold fossil without having some sort of a cast. This is where it's like 5.5 sort of a thing, because really you can't have much for a mold without a cast. But a cast is the fossilized copy of an organism made when a mold of an organism is filled with sediment and material. So what happens is that this is the actual like Jell-O itself in the end game. So a mold is like the actual like fluted pan. The cast is what comes out of the fluted pan. So that's kind of the idea behind that one. So this is where it's like 5.5, because molds and casts tend to go hand in hand, if that makes sense. So mineral replacements. We know that in order to create a mineral, it has to once be dissolved within water, whether it's cold or hot solution, and then given enough time to sit there and actually start to form those crystals, just like if you were to think of rock candy or the borax sort of like ornaments, things like that. The same thing can happen with calcium in shells and bones and things like that. Is if you add the right type of minerals to it, the minerals then can replace what was once the hard material. So for this example in this picture, a shell, which is normally made of silica and calcium and things like that, is now being replaced with quartz because it was able to sit in the solution that the minerals were once dissolved in. The water evaporated off and they just kind of clung to this because it had the best structure, enough support to be able to give it. So that's a mineral replacement. So I have an example of a ammonite fossil here that is now considered like a geode because it has the amethyst and the quartz building up around where the shell once was. So ours would be a mineral replacement fossil rather than anything else. So kind of cool. I will post a picture of it at the end of this just so you can kind of see like, this is what she is talking about. And then finally there's trace fossils. Now trace fossils is essentially a way to see how behavior of an organism once was. So what this means is like if in this case we have some sort of a four-legged animal that was walking, their footprints got left in this mud, eventually and over a relatively quick period of time, the water from that area was completely evaporated off and it hardened and solidified into solid rock. But what we're able to get from trace fossils is being able to see how this particular animal moved. Now, I can say it is a four-legged organism because of the way that the steps are displaced. I can tell you that it's a relatively light organism because the imprints themselves are not very deep. The one like in the corner of my screen, I'm trying to my screen is backwards, like over here, yes, is a little bit deeper, but if you look at the rest of them, they're fairly light on their feet, things like that. I can't, but people who are good at math could then take the distance in between the footsteps and get a relative height for what this organism was and a relative weight because of the displacement of the feet and things like that. So you're actually able to get a lot from just some footprints. The coprolite in my room is an example of a trace fossil because it can tell you what kind of an organism once excreted it. You could tell that the one that in my room specifically is smaller, so it must have come from a much smaller organism at one point in time. Things like that. Sometimes you do get other remains in there, so then you can see what kind of a diet these organisms have and things like that. It's really, you can learn so much from what looks like so little. So those are just an example of trace fossils. Now, why do we go through all of this? So we look at fossils to get an idea of the ancient environments that they came from. Obviously, back when the dinosaurs roamed, we didn't have historians, we didn't have cartographers, we didn't have people to document everything that was going on. So we're relying on what now remains as our way of writing the history books. So paleontologists use fossils to understand these ancient environments and their climates. They're able to compare past organisms with organisms of today. Again, coming back to that trilobite versus the horseshoe crab sort of a thing, we are able to tell that the first living organisms that once were on Earth were completely marine bound, meaning they didn't leave the water and they were single cellular organisms. And then from there, we were able to develop into multicellular organisms, again, marine bound. And then eventually we worked our way onto land. We know based off of this what the world once potentially looked like because of the type of organisms that ruled at that time. And we'll talk more about like ruling at that time when we talk about relative age dating. But these are just examples of why we look at fossils and why it can be so interesting, because essentially you're writing the story by looking at these fossils, because they're not here to necessarily tell their part of the story. You are filling in the blanks for them. So on that really sappy note, that's all I have. Make sure you have completed your notes for today. Get them submitted. Make sure you check out the exit slip and get that completed for me, please and thank you. And if you have any questions, please reach out. Let me know. Awesome. Have a great day, you guys.